Hello, and we are now continuing week 4 and 5, and hopefully week 4 and 5 addendum. So now we're going to get into regression diagnostics. Later on, we will use the simulation to check what happens when we break linear model assumptions for BLUE, or Best Linear Unbiased Estimator. But for the usual cases with real data, we would like to use regression diagnostics to check if we have certain problems with the regression. And if there are these problems, then maybe we can think of ways in order to solve them. So I'll focus on the cross-section case here and defer to time series to later if we have time. Much of the time, we'll use the residuals U to diagnose the regression. I guess the most practical concept that we will learn right now is called a leverage. So there's a concept of leverage of an individual observation. An individual observation has leverage when it is an outlier on the y or x axis, and that has an effect on the size of the coefficients. So in order to have an effect on the size of the coefficient, you'll have to have not just to be an outlier on the x-axis, but you'll also have to be an outlier on the y value as well. And the closer it is to x bar, the mean, the less leverage it has. So the highest leverage are the ones with a high x bar and a high y value for that observation. When you're far away from x bar and when you're far away from y bar, basically. So here we've got the ASCOMB regression, and we've got the plot here that we did before, and we've isolated Alaska here. So we look at the plot again. Alaska is an outlier in both y and x. It has a likelihood to have leverage because it's not close to the mean of x. So we can use the regression diagnostics plot to calculate or look at Cook's distance. So we can run this one, plot reg4. So let's do that right now. Here I've got reg, which is the regression, and as usual, you have coefficients. So we're going to do what that suggested, which is this, which will give you Cook's distance. The higher it is, if it's greater than 0.2, then it's really an outlier, or not just an outlier, but an observation with leverage. And if you have leverage, the higher the leverage is, the higher the effect on the coefficients will be. All right, so we expect that the coefficient will change by 50% because of the size of Cook's distance, which is here. Okay, so what do you do if you have observations with high leverage? It depends. If it's a mistake in the data input, you try to delete it. Now in the homework, we'll try that. If it's not a mistake, most likely you are misspecifying your model in some way, right? And there are many ways to check whether your model is misspecified. Either it's nonlinear, right? So you can change your x values and your y values by applying transformations to x and y and see if that works. Another reason really is that this residual here, it depends on some other variable that's not in the simple OLS. So if you introduce other things which can explain why Alaska in particular has a high education spending for its level of income, then that can probably work, right? So specifically, there are two other regressions in the ASCOMB dataset, urban and youth. And you might think to yourself, okay, it's possible that Alaska has a high education spending per capita because they also have a lot of young people in the population. So maybe that will help explain this residual. So this residual is really about a variable which really should be there, but it isn't, right? So those are examples of misspecification. So here we include two other regressions. In fact, this is our first encounter with a multiple regression. As you can see, multiple and the sample regression is basically the same. You just add the regressors one by one on the right here. So instead of just income, you add plus young and plus urban. And it's basically the same thing, right? And I'm calling it reg 2 because this is our second regression. You can call it whatever you want, of course. And here we find that the coefficients are all significant. Okay. There are more young people, the more you spend on education. And the more urban it is, the less you spend on education. No. So what is the effect on the leverage of AK? So now the leverage is much smaller. So before, if you remember, this is more than this is almost 0.6. But now, after you include the variables, it becomes much more in line with everyone else, 0.2. So it really helps to explain that extra residual for Alaska. Okay. Next is an important diagnostic is residuals against X, or even residuals against predicted. That's also equivalent. Okay. So notice that our population assumption is this, that the mean of E conditional on the covariates is equal to 0. Now, usually we only have a sample, and we impose that the mean of U conditional on X is 0 on the sample. So we know that if we average all of these residuals, it's going to equal to 0. But what you should look at is the pattern of the residuals over the space of income, or Y hat, or the predicted Ys. You use predicted Ys basically if it's multiple regression, if you have many X's. If you only have one X, then it becomes easier to use that one X to plot the residuals against income. So as you can see here, it's a good spread. So what you'd like to do is, what you're looking for are areas where there are only positive or negative residuals, like really these patterns and how the residuals are related to income. Okay, in these cases, then you've got a misspecification problem on your hands, because the residuals are related to either the predicted Y or the regressor. And so there's this underlying issue that sort of like, there's underlying pattern in the residuals that are being affected by other variables, which are also related to the variables that you've got here. Okay, because what you want really is over the entire X is like an even spread of dots. So mainly this is fine because you've got, especially in the center, which is the mean of income. In this center area, you've got a lot of dots above and you've got dots below 0. And the lowest line here is basically equal to 0 throughout. So the residuals against X for the SCOMB is pretty okay. If there is no real pattern of the dots around 0, around 0. This is 0, around 0. So there's some positive and there's some negative within the center of your X variable, which is income. Okay. The same way for predicted Y, if there are no patterns in the residuals over the value of Y, then that's good. And that's what you're looking for. So this is an example of okay. You can also look at the residual versus X plot to look for heteroscedasticity. So another factor leading to the efficiency of the linear model is constant variance, which is this. This is one of the assumptions of blue. Plotting the errors against X or Y hat can also help look for variance at different values of X. So we should look at patterns where the spread of the residual is increasing over X. So if you can imagine here, if you can take a look at as X is going up, the variance or the dots, the width, the variance basically of the residual, like you can see dots up here very high and then dots down here, and then the spread becomes wider and wider as income goes up, right? So that is evidence for heteroscedasticity, because the variance of E is not constant over X. Okay. Now the effect of heteroscedasticity is that the confidence errors may be too small or too large, so conclusions on inference can be misleading. So later on in the course, hopefully we'll have time at the very end, we'll try to come up with solutions in R for heteroscedasticity. Having said that, heteroscedasticity is not a major something you should really concern yourself with, especially since there are these interesting solutions already for heteroscedasticity called robust standard errors, which we'll introduce at the end. So it's really more towards residuals against X, looking for these patterns of the relationship between the residual and y hat or any of your x's. That's a problem of misspecification. And then finally, let's talk about the interpretation of a continuous variable coefficient. So this is our basic OLS, simple OLS. If x is continuous, then the coefficient beta is the marginal effect of one unit increase in x. So again, this is something, this is a review of your class, your theory class. You should know this by now, right? We can non-linearize our model, and this is what we were talking about when it comes to transformations of the x and y, by applying functions to x and y. So one of the popular ones is basically to log or get the natural log of y or x. Okay, so there are a couple of things that's important to think about when it comes to these things. So in the next slide, we will find how logging will help with the residuals issue. When you plot the residuals against x, you'll find that if you don't transform it, then there's going to be this pattern in the residual against the predicted y or x. Okay. It can also help with heteroscedasticity because the large values will tend to become smaller, okay, when you log them because of the shape of the log function. So it helps with heteroscedasticity and it helps with potential misspecification. So these are things that you can try. There is an effect on the interpretation of the coefficient. So now it's not just a unit increase in x. If you have a double log model, which is this d log y over d log x, that's beta, which is equivalent now to what's called the elasticity of y with respect to x. Okay. Oh, by the way, this is what I said. Creating nonlinear functions x and y can fix issues in the linearity assumption, which creates misspecification, biases the coefficients, and you can see that in the residual plots. And I did not mention here the heteroscedasticity, which is also an issue. So you might want to do that for that as well. Elasticity, just to end, because this is the last slide, and elasticity should be something that you should know about. So an elasticity is the percent change in y with respect to the percent change in x. So again, this is basic economic theory, economic results. What a demand elasticity is, or supply elasticity, or any elasticity is just a percent change in the numerator with respect to a change in the percent change in the denominator, which is the value of the beta. All right, so that's week 4 and 5. Let's talk about the addendum. So I did the addendum because I want to make sure that everyone knows what unbiasedness is and consistency, okay, because that will play a role in the end of the course. And that's something to remember because the OLS, what you're after really is to make sure that your regression and your estimates are unbiased and consistent. So what is bias? Bias is when the expected value of the estimator is, is not equal to the true population variable. I will upload this corrected one because that's important. Because bias, right? The graph on the right indicates low versus high bias. So here's the bias. And high variance versus low variance, right? So what we'd like is a low bias and low variance estimator so that every time you collect samples, the estimator will give you an estimate which is near the true population value, which is the red dot. Whereas if under high bias, even under repeated sampling, you do take 10 samples here and then another 10 samples there, and then you compute the coefficients each time, right? It will be under a low variance, true in this situation, but it will be far away from the population variable, the true population variable. So even though you keep sampling over multiple samples and you average over the estimates over for each of the multiple samples, then the average will be far away. So that's bias. right? Whereas this is an unbiased estimator. If you sample here, get an estimate, sample there, get an estimate, then you take an average over all the samples, it will be close to the population value. So OLS is unbiased under the BLU assumptions, which is this one, which is kind of like this. This is the mental image that you should have when you're thinking about bias, okay, or low bias. Now, a consistency of an estimator is a sort of a large sample conceptual understanding of it. So you've got consistencies when you increase the sample size, the estimator converges to the population parameter. So it is said that the estimator converges in probability, quote unquote, that's a technical term, converges in probability to the true population parameter. So what this means in practice is that the mean moves toward the population parameter and the variance narrows as n moves to infinity. If an estimator is already unbiased, so that means the mean is already on the population mean, this just means that the variance narrows as you get more larger sample size. So consistency is really about what happens when you increase the sample size. And when you increase the sample size, you move towards the true population value and the variance of the estimator narrows so that at the limit, you're really pinpointing the population variable, population estimate. So this is an example coming from Wikipedia of consistency. So you've got these estimators here, 1, 2, and 3. These are sample sizes. So given a small sample size, here's your distribution, right, of the estimates. Okay. The true population value is 4, and it seems that if the population, if your sample size is low, you're quite far from 4. But as you increase your population size, or sorry, your sample size from 1 to 2 to 3, you move from this really spread out one to this less spread out one to this green one, and finally to this big T, which is literally this distribution, which is sitting on the population value with a tiny variance here. And that is consistency, which is the hope that as you increase the population size, you are narrowing that variance. But remember, since OLS is blue, an OLS estimator basically is all of these curves, but all of them have a mean of 4. So you can imagine multiple curves, fewer observations being more spread out, but all of them centered around 4. Okay, whereas this is a more general case where as you increase the sample size, the mean, which starts at 3 and then goes to 3.25, then it goes to 3.75, then 3.9, and then 4. The mean goes towards the true population variable, and the distribution itself becomes quite narrow, quite tight around the true population value. So that's a picture what the consistency means, right? Which is a statement about what happens when the population or the sample size increases. All right, so now let's try to look at residual plots again. So in the earlier slides, we showed a picture of an OK residual plot. But what about a non-OK residual plot? So we have an additional code here, which is linear regression 1 OLS residual analysis.R. And here are the Gapminder codes, which are there in the code here. I just copied them here. So you can run them, and at the end, it will result in a ggplot. Okay. And you will look at the following, right? You will get the residuals first, and then you will ggplot the residuals to population. And here is a ggplot of GDP to population. So here's the ggplot of that residuals to population. As you can see here, most of the world has a fairly manageable population here. This is, and only some countries in the world have this size. So it's millions, and then this is like 10 millions, tens of millions, right? and this is like 100 millions already. Okay. So what would happen if you were to plot, for example, ln population to residuals, to make it clear? Because an ln will really help with the heteroscedasticity, right? With the extreme values of ln pop, it will tend to compress it. So recall that this is exactly the same, huh? Same regression, same resid. We're just changing the population from population to ln population. And what will happen here is you can see clearly a relationship between population and the residual. It's clearly going up, right? In this level, at low population, okay, the data is below 0. And when the population is above the mean, the residual is above 0. So that is an example of a very, very clear issue with the residual plot. So this is proof that the regression that we did here, which is simply GDP to population, will be misspecified. Okay. So that's just an example of a misspecified plot. Now, other ways to use residual plots, like we said, we can use it to check for heteroscedasticity, to check if the residual variance is increasing in X or the predicted variable Y hat, predicted values. So see the code here, and here's just a picture of an example of a residual plot where the variance grows as X goes up. So this is another example of a problematic residual plot. Again, for heteroscedasticity, there are the solutions. Either you take logs, okay, which probably might handle the heteroscedasticity issue. So you take logs of the original regression, the Y and the X variables, and then you plot the residual against the predicted or the X again. Okay. Another solution, which we'll discuss at the very end, is what's called robust standard errors, which is basically a package that you can load and you can run your regression on, and it'll give you better standard errors that will take into consideration the heteroscedasticity in your data. All right, that's it, and see you next time for multiple regression and discussion on using categorical variables in linear regression, multiple linear regression. Bye.